Okay, let's talk about resistance. Resistance, we've already learned. You can have a resistor in a circuit, and it's got resistance. And we found that, for instance, if you put two resistors in a row, that would make a bigger resistor, right? So if this is R1 and this is R2, then the total resistance is R1 plus R2. And then this tells us that resistance is a property of the geometry, right? So if the resistor is made longer, it's a higher resistance. In the same way, think about what happens if I change another geometry of the resistor. Think of the resistor as a wire with resistance, right? And so if I make it longer, we call that L. The longer it is, the more resistance we have. Now what if I make it have a bigger cross-sectional area? Right, so we'll call this A1 and this A2. A2 is bigger than A1, still the same length. Would it have a bigger resistance to the flow of electrons or the smaller resistance to the flow of electrons? Remember, we've defined resistance as resistance to the flow of current through a wire. I'm not going to write that down. We've already defined it, the resistance to the flow of current through a wire. And so if we give it a bigger cross-sectional area, what is that going to do to the resistance? And the answer is the resistance will go down. And the qualitative explanation of that is because the current has more paths to take, so it finds it easier to get through the resistor. So resistance should be proportional to length and should be inversely proportional to area. And we do find that that is indeed true. And yes, it could be inversely proportional to something else, but area squared or, whatever, but some other factor of area. But we find, or we define, either find or defined resistance to be proportional to 1 over the area. And think about what is something else that resistance should be dependent on. Is dependent on the geometry. What else is it dependent on? Think about it. Right? It should also be dependent on the properties of the material. So it depends on the material properties themselves, material properties. In other words, for a given cross-sectional area and length of copper, it has a smaller resistance than the same cross-sectional area and length of, let's say, actually aluminum. Copper, it does have a smaller resistance than aluminum, or than glass, right? If we can make a resistor out of glass, sure. But if you take the same geometry, the resistance of copper is going to be smaller. There's one other typical thing that resistance is a property of that most students know, and but that's built into the material properties, and that's the temperature. So it is also dependent on temperature, but that's built into the material properties. A material has a certain temperature, has a certain pressure. No, well, anyway, temperature is another property. And those material properties are called, the material property is called the resistivity. Whoops, I gotta write it. The resistivity is the Greek letter, the small Greek letter rho, and the resistivity is the measure of resistance that's dependent on just the material properties but not the geometry of the material. So if we put all this together, the resistance is equal to rho L over A. So rho is the proportionality constant for the geometry, and it's material dependent. So the resistivity of copper is smaller than the resistivity of glass. The resistivity of silver is smaller than the resistivity of gold. I knew that. You didn't. But resistivity is not dependent on the geometry. So we can say, hey, let's say we want a resistor. We want a resistance of 100 ohms, and I need it to fit into a certain geometry, length and cross-sectional area. So now I can look for a material that has a resistivity such that if I take a certain length and a certain cross-sectional area, I get the resistance that we look for, the 100 ohms or whatever. But resistivity, right, so it doesn't matter how big the lump, let's say I'm just using copper, it doesn't matter how big the lump of copper is. It doesn't matter if I have a little tiny bit of copper or a big old lump of copper. Doesn't matter what shape it is, that's an odd shape. That they both have the same resistivity, but they would have, if I tried to flow current through it, they would both have a different resistance because they have a different length and cross-sectional area. They have a different geometry. So let's look at units. If the units of resistance is the ohm, or the MKS unit, the Greek letter, capital Greek letter omega, or horseshoe. Horseshoe is not a Greek letter, but it's still a horseshoe. Then, and the MKS unit of, let me write this out, L over A. MKS unit of length is meters and area is meter squared. Then the MKS unit of resistivity must be the ohm times meter squared divided by meter. So it's the ohm meter, or the ohm meter. Oh man, I was gloating earlier that I knew something that you didn't, but I did say something that was incorrect. The resistivity of copper, I just looked up the numbers, the resistivity of copper is 1.7, just to give you a sense of the numbers, times 10 to the minus 8 ohm meters. The resistivity of silver is actually smaller than copper. I guess the reason why we don't make wires out of silver is because it's expensive, not because it has a higher resistivity. In any case, that's the resistivity of copper. Let's look at something else. The resistivity of aluminum. Actually, I'm not sure. I think it was aluminum that I said was higher. Maybe I was right, because that is right. The resistivity of aluminum is 2.7 times 10 to the minus 8. Whoops, that's a 10 to the minus 8. 10. I'm going to stop and fix that. So these are things that have relatively low resistivities that we use for wires. And things that we typically use as insulators should therefore, right, have a high resistivity. So let's look at the resistivity of rubber. There's different kinds of rubber, but the resistivity of rubber is 7.5, can you guess, times 10 to the 17th ohm meter. So it's a very different scale of number, 10 to the 25th times. So an easy example, let's take a copper wire, typical copper wire we find in lab. Let's say it has a resistivity that we looked up, and ask what's the resistance if the wire has a cross-sectional area of 10 to the minus 6 square meters. Again, that's about a 1 millimeter by 1 millimeter if it was a square cross-sectional area. That seems like a reasonable size of a wire. I guess a wire could be a lot bigger than that. And a length of 1 meter, typical wire you would find, and what's the resistance of that wire? The resistance is resistivity, L over A, and it's just a straightforward plug-in. And note that the units work out, that the meters squared on top cancels with the meter squared on the bottom, and what we're left with is 0.017 ohms. That seems reasonable for a wire, right? You want the wires to be low resistance, ideally zero resistance, but unless they're superconductors, they're only going to be low resistance compared to the kind of resistors we use in lab, hundreds of ohms, thousands of ohms, tens of thousands of ohms. So the resistance is pretty low. And note that this is 0.017 ohms for a 1 meter wire, so that is 0.017 ohms per meter. So now we can just scale that up and say, let's say that I have a wire that runs 10,000 meters, right, from the power company to my house, 10,000 meters, that's 6 miles, times 0.01 is going to be, the resistance is 170 ohms if it's running 6 miles. Now, of course, if you're running a wire from the power company to your house, it's going to have a larger cross-sectional area, but regardless, that's just an example. I want to look a little closer at resistivity. What I said earlier, and I might have said it a little unclearly, is that temperature is another thing that we tend to understand the resistance is dependent on, but the temperature is built into the resistivity. In other words, resistivity is material property dependent, and one of those properties is temperature. So resistivity tends to go as, empirically, it goes as linearly with temperature, where A and B are constants and T is temperature. So resistivity goes linearly with temperature, not proportional, right? If it was proportional, it would be resistivity is A times T, but it's linearly A times T plus B. Again, A and B are some arbitrary constants. T is temperature. I do challenge you to look at the book's definition of resistivity as a function of temperature and see that the way the book defines it is the same. It is a constant times T plus a constant. It just defines it a slightly different combination of constants, but it really is the same. It's still linear. So this actually means that, again, since resistance is resistivity times L over A, that nothing is truly ohmic. What do I mean by that? Nothing is truly ohmic. Remember what ohmic means. Ohmic means that if you plot V versus I and you increase the current, if you increase, V versus I, and you increase the voltage, therefore increasing the current, the voltage versus current is a line. Here, either V or I could be the independent variable. It doesn't matter. But if it's linear, then it's ohmic. If it's nonlinear, then it's not ohmic. So if indeed the two relationships I told you are always the case, then nothing could actually be truly ohmic, because as you increase the current, let me change the color. As you increase the current, and if it's got a resistance, it is by definition resisting the flow of the current, so it must be heating up. By definition, that if it's resisting the flow of current, it means friction. It must be heating up. If it's heating up, it's changing temperature, and therefore the resistance is not constant, so it can't be linear. But if over the range of currents, the resistivity really doesn't change very much, then you're not going to see that nonlinearity, and it's going to be approximately linear over the range of currents that we're interested. Also, right, the smaller this A, the closer the less dependent on temperature it is, right? So if that constant in front of the temperature is small, the less dependent on temperature. If it's big, the more dependent on temperature. So nothing's truly ohmic, but it may be relatively ohmic over a small range. Over the entire range of voltages and currents, absolutely not. Nothing's ohmic. But over a smaller range, it may be approximately linear, and then we call it ohmic. That being said, don't tell me if we ask in a lab, is it ohmic or is it not ohmic, that nothing's ohmic, because if it is linear over the range that we're looking at, or if it appears to be linear, then it is ohmic. That's how we define it to be ohmic. It may not be precisely ohmic, but ohmic is, let's just say ohmic is an approximation, a linear approximation. If it's linear, if it looks linear, then we're going to call it ohmic. So why shouldn't you try to borrow money from a leprechaun? Because they're always a little short. So I'm just going to mention one other thing worth knowing, but there's nothing more we need to do with it, because if we understand resistance, we must also understand conductance. So there is a quantity called conductance. What is conductance? Conductance or conductivity, two different things, but similar in the same way resistance and resistivity are similar. Conductance and conductivity is how well does a material conduct current. Resistivity and resistance is a measure of how well a material resists current. So once you understand one, you understand the other, because conductance is 1 over resistance, and conductivity is 1 over resistivity. So we don't need to say any more about it, except just to define them. But I particularly like bringing it up because this is where physicists get a little funny. Remember that the units of resistance are the ohm. So what are the units of conductance? The units of conductance are 1 over the ohm, right? And that is defined as, can you guess? I'm sure you can't guess, but do you know? It's defined as the mho. Okay, it really is. Mho, M-H-O, is the ohm spelled backwards. So that was either physicists running out of units or trying to be funny. But the unit of conductance is the mho. So the last thing we need to talk about before we can get back to circuit analysis, when I say get back to circuit analysis, is we've already done circuit analysis in lab, which is good because now we're catching up with that, and we can put together the theory and the practice. But the last thing that we want to talk about is power. We talked about power in lab, so now let's go ahead and remember what power is and define it for a circuit. Remember that power is a measure of energy over time, So if we're doing work on something, it's the amount of work that we do per unit time, or if something is using energy, it's the amount of energy per unit time. So power is energy over time, and the units of power are joules per second, or a watt, which is abbreviated a capital W, power. So probably light bulbs, right? For example, you have a 100-watt light bulb, and so a 100-watt light bulb means the light bulb is using 100 joules per second of energy. Or you might be interested in cars, and let's say that you have a car engine where you're told the power is 25 horsepower. Well, what is a horsepower, right? That's as if you had 25 horses pulling your car. Sort of, maybe, I don't know. But anyway, a horsepower is actually just another unit of power. I'm sorry, a horsepower is just another unit of power. Like watt is the MKS unit, but horsepower is a different unit. So 1 horsepower is 746 watts. So we've got 746 watts over 1 horsepower. Gives us 18,650 watts, or 18,650 joules per second. So this is the amount of, for a car, maybe it's the amount of energy that it uses, or maybe it's the amount of work that it produces, right? It tells you how fast, it really tells you how fast the car can accelerate. How powerful the engine is really has to do with how fast the car can accelerate. And it does generally mean that a car can end up going faster also. But if two cars both get to 100 miles an hour, if one of them can get to 100 miles an hour faster, then it's got a higher power. It can expend energy quicker than a car that takes longer to get to 100 miles an hour. So in a circuit, power in a circuit is equal to current times, potential difference. Let me change that. Oops. Okay, I might be repeating myself, but I'm unclear if I was recording when I just recording what I just said. So I'm going to say it again. Power is I times potential difference, where it is more often written as I times V. But remember, but in this case, V is voltage because we're talking about a circuit. And voltage is really a potential difference. So I told you, if I'm talking potential difference, I'm always going to write potential difference. And so this delta V is voltage or potential difference. And if you see it written as IV, you just have to understand the context. That means I times potential difference. Let's just see how these units work out. The units are coulombs per second times potential difference, which is joules per coulomb, and so what we're left with in units is joules per second, or watts. I didn't just prove that P is equal to I times delta V, but I showed how the units work out. So for a circuit that is that has a certain potential, perhaps has a voltage source, which has a potential difference of delta V, and that voltage source is providing a current I. Let's go ahead and draw that. The power being provided by that voltage source is I times delta V. If that then goes, or if we have a collection of resistors or anything else in the circuit, but let's start with resistors, and each of those resistors has a delta V which is different across it, right? Different from each other resistor. And a current through it, which, these currents may be different, I1, and there's a current through this resistor, we can call that I. Then the power used by that resistor is the current through the resistor times the delta V across the resistor, right? So this is the power supplied by the power supply, this is the power used by a resistor. It's all I times delta V, we just have to be careful about which I and which delta V. For that reason, it's often more useful to talk about the power through a resistor if I've got a resistor and it's attached to a circuit that's not shown, and that resistor has a resistance R and a current through it. I'll call that I sub R. since the power is equal to the current through the resistor times the potential difference across the resistor, and we know that the potential difference across the resistor is I through the resistor times R, therefore we can go ahead and plug that in and say that, oh look, the power is I sub R, sorry, the current through the resistor times the current through the resistor times R, so we've got I squared R. So the power used by a resistor is I squared R. It is also I delta V, but it's I squared R as well. Just that's gotten to that, we get to that using Ohm's law. For a given, and just to be complete, for a given problem, we may not know the current through something. We may know the potential difference in the resistance, so we can go ahead and substitute in for the current in P equals IV using Ohm's law, V equals IR. If we substitute in for the current, you can see that therefore the third form of power can be written as delta V squared over R if we don't know the current and we know the potential difference in the resistance. You don't have to remember all three of these, right? Because it's just one equation, boom, 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 that one. And then we can use Ohm's law to make substitutions to figure out the other two. So let's just do an example. Let's say that I have a 3-volt power supply hooked up to two resistors, 100 ohm and 200 ohm resistors, and ask, what is the power supplied by the power supply and what is the power used by each resistor? So I want to know the power, So I want to know the power, which I'll call P delta V, P sub delta V, supplied by the power supply, P sub R1, power used by resistor 1, P sub R2, power used by R2. Various ways that we could do this. Let me do this the very easiest way if you really are knowledgeable about simple circuits, and then let me do it the way that you would do it out really, in detail. So the very easiest way is to look at this and understand that this is a voltage divider and that these two resistors, I just circled them in yellow, obviously you knew they were there, that these two resistors divide the 3 volts. One resistor is going to have a smaller voltage than the other, right? And that's because they have the same current, I times R, right? IR1 is going to be smaller than IR2 because they have the same current, and the IR1 plus IR2 must equal 3 volts. So you can look at this, and what I really just did was did it out the long way without writing it down, but you can look at this and see that the potential difference across R1 must be 1 volt and the potential difference across R2 must be 2 volts because it's a voltage divider. It divides it into a proportion of the resistances. Once we recognize that, then we can say that therefore the power, I keep doing that. The power for R1 is delta V R1 squared divided by R1. Just plug in to V squared over R, or delta V squared over R, and you get 0.01 watts. Do the same thing for R2, and you get 0.02 watts. And therefore, I'm going to stay on this page just for a second. So therefore, the total power is going to be, better be the power of R1 plus the power of R2, which is 0.03 watts. So the total power supplied is going to be the sum of the powers used. This total power supplied better all be used up. Otherwise, where would it go? It's energy per unit time. It's energy conservation, right? So this is an energy conservation issue. So we didn't even need to calculate the power supplied by the 3-volt power supply, because if we just calculate the total power used, that's the power supplied, 0.03 watts. So that was the quickest way, but not the most straightforward. Let's go ahead and do a really rote sort of let's go through the numbers way. So if we draw on the circuit, and let's just think about let's calculate the current. We need to calculate the current through the circuit, and there's various ways of doing that, but you might recognize that the equivalent resistance is R1 plus R2, which is 300 ohms. So therefore, delta V equals IR. The equivalent resistance and so therefore the current is 3 volts over 300 ohms, which is going to be 0.01 units of current, volt per ohm or amp. So from that we can go immediately to the power supplied by the power supply is going to be I delta V, the current from the power supply times the potential difference of the power supply. So it's going to be 0.01 amps times 3 volts, which is 0.03 watts. Okay, 0.03 watts. Oops. Okay, so that was what we figured out before. That matches. Good, check. And then we can say that the power supplied to R1 is I squared R1. The current through R1 squared times R1, which is 0.01 amps squared times 100 ohms, which is equal to 0.01 watts. Check. And the power supplied to resistor 2 is the current through resistor 2 squared times resistor 2, which is 0.02 watts. Check. Okay, so that's just only a slightly longer way, but that's calculating the current in order to get to the powers. So we now move on to the circuits chapter, and in the circuits chapter we'll talk about the Kirchhoff's rules and how we combine resistors and capacitors in equivalent circuits. So the circuits chapter is going to be pretty quick because we've actually already done everything. We now just need to formalize it and move on to magnetism. But the circuits chapter will be the next couple classes when we meet again.